There are all sorts of waves and a lot of different ways to describe them. So here's a quick review. A transverse wave has propagation of the wave perpendicular to the displacement from equilibrium. This means that the wave part that oscillates is actually perpendicular to the direction that the wave is going to move. A typical example would be an electromagnetic wave, because we have electrical and magnetic fields perpendicular to the direction the light actually moves. Another transverse wave would be like the waves on the surface of the ocean. The water goes up and down, but the wave itself is actually moving to the right. A longitudinal wave has disturbances that are parallel to the direction of the wave is moving. This means that we have a buildup of disturbances in the same dimension as the velocity. The best example we have is sound, where we have buildups of pressure in different locations that move in the same direction as the velocity. Now we can draw waves as a function of time or of space, and these plots will give us different information. Be careful. If you look at a plot of amplitude versus time, between each peak or trough represents the period. But if you look at amplitude versus position, the peak or trough difference corresponds to a wavelength. So be careful when you look at these two different plots. The last thing is that we can represent any kind of wave using wavefronts. So each of these wavefronts will correspond to a peak in our amplitude. So this is the highest possible pressure or height or whatever you want to look at. In between, right in the middle, will correspond to the trough. Now the direction it's moving, we can just draw a perpendicular ray to indicate which direction that part of the wave is moving at any moment.